In the previous video, I introduced you to Archimedes' Principle. Archimedes' Principle concerns the buoyant force, or the buoyancy force, which is the net force exerted on an object immersed in a fluid by the pressure of the surrounding fluid. Let's say, for example, I have some object here which is immersed in a fluid. I've drawn in all these squiggly arrows to represent the pushes of the surrounding pressure on that object. The net force resulting from all of those pressure pushes would be the buoyancy force. The buoyancy force would point upward, and according to Archimedes' principle, the strength of that buoyancy force would be equal to the weight of whatever fluid was being displaced by this object. In this video, we're going to apply Archimedes' principle to an example problem. So over here, I have the example problem set up. I have an aluminum sphere, which is immersed in water. Aluminum is more dense than water, so to keep the aluminum from sinking to the bottom of the water container, we also have a string which connects the aluminum sphere to the ceiling here. We would like to figure out the tension in the string. We are given the radius of the aluminum sphere, and we also know the density of aluminum and the density of water. The density of aluminum is 2.7 grams per cubic centimeter, and the density of water is 1 gram per cubic centimeter. So we're going to solve this problem by drawing a force diagram for the aluminum sphere. So why don't you give this a shot? You may choose to make a copy of the aluminum sphere all by itself somewhere else in your notes, and then try to draw in all the force vectors acting on the aluminum sphere. Once you've given that a shot, rejoin the video. So doing the force diagram now, as usual, we have the gravitational force acting on the aluminum sphere. The magnitude of that would be the mass of the aluminum sphere multiplied by little g, as usual. We have the tension in the string, magnitude T. And then we also have the buoyancy force. The buoyancy force would point upward as well. According to Archimedes' principle, the strength of the buoyancy force would equal the weight of the blob of water, which would be here if the aluminum sphere was not. So I'm going to say that the magnitude of the buoyancy force is equal to the mass of the displaced water, dW for short, times g, the free fall acceleration. And to be clear, I'll come down here and write that dW stands for the displaced water. Let's proceed as usual. We're going to start by putting in a y-axis. Now, in this problem, there's nothing happening in the horizontal direction, so I only need my y-axis pointing upward in the vertical. And then, as usual, we can set up our grid where we're just going to have the one row for the y components of the forces. So the y component of the gravitational force is minus the mass of the aluminum sphere times little g. The magnitude of the buoyant force is the mass of the displaced water times little g. Magnitude of the tension force is T. Now, the aluminum sphere is just sitting there. It's not going anywhere. It's not accelerating. So we can say that the sum of the y components of the forces acting on the sphere is 0. So let's just add up the y components now. We have minus the mass of the aluminum times little g, plus the mass of the displaced water times little g, plus tension equals 0. Now we can do an algebraic step to solve for tension. We have tension equals mass of the aluminum minus the mass of the displaced water times little g. Now, to finish the problem and get the tension, we have to figure out the mass of the aluminum sphere and also the mass of the displaced water. Here, we can use something which we learned earlier in the module, which is that the density of an object is defined as the mass of the object divided by the volume which it occupies. So using this, we can say that the mass of the aluminum sphere is equal to the density of aluminum multiplied by the volume of the sphere. Here we need the formula for the volume of the sphere. The volume of a sphere is 4 pi over 3 multiplied by the radius of the sphere cubed. We can do something similar for the displaced water. The mass of the displaced water would equal the density of water times the volume of the displaced water. Now, what is the volume of the displaced water? Well, displaced water refers to the blob of water which would be here if the aluminum sphere was not. So the volume of the displaced water is exactly equal to the volume of the aluminum sphere, which is actually sitting there. In other words, the volume of the displaced water is 4 pi over 3 times the cube of the radius of the aluminum sphere. Let's call these equations here 1, 2, and 3. So we're going to put 2 and 3 into 1. That gives us tension equals, all right, mass of aluminum would be density of aluminum times 4 pi over 3 r cubed minus mass of the displaced water would be density water times 4 pi over 3 radius cubed, all of that times little g. Now, let's simplify this expression by factoring out 4 pi over 3 times radius cubed. So then we have that multiplied by density aluminum minus density water times g. Now, notice that the given quantities here are in terms of what we call CGS units, grams, centimeters, and seconds. So I'm going to continue using CGS units as we make the substitutions here. So we then have tension equals 4 pi over 3 radius 2 centimeters cubed. Then we have the difference of the two densities, so 2.7 grams per cubic centimeter minus 1 gram per cubic centimeter, then times little g, which would be 980 centimeters per second squared. So this is a multiplication. I just didn't have room for the g over here. Now, just plugging all of this into the calculator, the numerical value I get is 5.58 times 10 to the 4. Now, let's look at the units. First, we have here centimeters cubed, then grams per cubic centimeter, and then here centimeters per second squared. So cancel centimeters cubed against centimeters cubed, and what we have here is grams centimeters per second squared. This is actually the CGS unit for force. It's known as a dyne. So the tension would be 5.58 times 10 to the 4 dynes. Now, if you would like to get this back in the MKS units that we're used to, you can use that a Newton is equal to 10 to the 5 dynes. And if you then use this conversion to get back into newtons, you would get that the tension is 0.558 newtons. So there we go. We have done our first example problem using Archimedes' principle.